Let's do another problem involving inflection points and concativity and minimum points and maximum points, and see if we can get a little bit more intuition of everything that's going on here. So our friend Akash sent me some more problems that he would like to see done, and these seem pretty good, so let's do them. So let's see. The first problem, it says g of x. It gives us this. G of x is equal to 3x to the fourth minus 4x to the third plus 2. And it says determine where the graph. Oh boy, the phone is ringing. The phone is ringing. I don't know who that is, so I'm not going to answer that phone. Anyway, it's probably a telemarketer. But anyway, so it says determine where the graph of the given function is increasing, decreasing, concave up, and concave down, then sketch it. So essentially, it says just figure out everything about this function and then draw it. So what's the first thing we should do? Well, let's figure out all of the critical points. Well, what are the critical points? Those are the points where the function either has a zero slope, so it's kind of flat at those points, or it has no derivative, so it's either a zero derivative or no derivative. How do we figure those out? Well, first we have to figure out the derivative and set it equal to 0. So what's the derivative? G prime of x is equal to, let's see, this is 12x to the third minus 12x squared plus 0. So that's the first derivative. And we're going to deal with the second derivative, so let me just write it down right now. So what's the second derivative? Maybe I'll do that in another color just for fun. G prime prime of x. Since our brains are in derivative mode, let's just do that. So it's 36x squared minus 24x. So let's figure out the critical points, or when the slope is equal to 0. So I'll call them CPs. Critical. Well, I'll just write down critical. So to find the critical points, we set the first derivative equal to 0. We're just trying to figure out when does the slope equal 0. So let me do it in the first derivative color that I chose. So let's set 12x to the third minus 12x squared is equal to 0. So we could factor out a 12x squared. So we get 12x squared times x minus 1 is equal to 0. And so what values of x make this equal to 0? Well, x could either be 0, because then this term would be 0. So we either get x is equal to 0, or x minus 1 is equal to 0. X minus 1 is equal to 0, or x is equal to 1. Right? Add 1 to both sides of that. So there we have 2 points where we know that the slope of the original function is 0. And let's figure out what they are, whether those are minimum points, maximum points, or inflection points, or whatever. So let's take the point x is equal to 0 first. So first of all, let's just know what the coordinate is. What's g of 0? So just so we know what the points are. So g of 0 is equal to what? G of 0, 0, 0, 2. And what's g of 1? G of 1 is equal to what? 3 minus 4, and minus 1 was 1. So actually, let's graph that. Let's graph it. So if this is, I'll draw it big, because this one seems like it might be nuanced. Let me draw it there. So that's my y-axis. That's my y-axis. And then let's say that, I'm going to do something different. Let me draw my y-axis. Let me draw it here. That's my y-axis. And this is my x-axis. That's my x-axis. And so what are the points that are the critical points? I'll do them in yellow. No, I'll do them in brown. So these are the 2 critical points. So one is 0, 2. So this is 0, and let's say that this is 2 right here. So that right there is the point 0, 2. And then the other interesting point is 1, 1. So if this is 1, y, this is about 1. So the other point is 1, 1. So this is 1, 1. Drop down here, 1, 1. So those are our critical points. So let's figure out if these are inflection points or whatever. So what is the second derivative at x is equal to 0? And I'll do that in the second derivative color. So g prime prime of 0 is equal to, let's put 0 here. We get 36 times 0 minus 24 times 0. It's equal to 0. So this must be, since the second derivative is 0, this is an inflection point. I'll just write. And what is an inflection point? Just to give you the intuition. An inflection point is when you go from either being concave upwards to being concave downwards, or you're going from concave downwards to concave upwards. And just as an intuition beyond that, what is concave upwards and downwards? Concave upwards means that over that interval, so if you're kind of in a bowl, the slope is always increasing. That's what concave upward means, right? Actually, I don't want to waste space here because I think I might need it. But concave upward means that. And if you look at every point, you see the slope is negative there. Then it becomes less negative. Then it becomes 0. Then it becomes more positive, even more positive. So the slope is increasing the entire time you're concave upward. And then similarly, the slope is decreasing the entire time you're concave downward, right? Because here the slope is really high, becomes a little lower, flattens out, becomes a little negative, more negative. So concave downward just means the slope just becomes more and more negative or decreases. And concave and an inflection point, having the second derivative equal to 0, just means you're switching from either concave downwards to upwards or vice versa. So that's an inflection point. And what is what is the second derivative at x is equal to 1? So this is an inflection point right here. Inflection point. That's an inflection point. So it's neither a minimum or a maximum. And then what is the second derivative at 1? G prime prime at 1 is equal to, and we just care whether it's positive or negative. We don't actually care about the actual value for what we're trying to do here. So take the second derivative, is 36 times 1 minus 24, so it equals 12. So it's positive, right? This is a positive number, so that means it's concave upwards. So what do we know? We know definitely that around 1, 1, we are concave upwards. So we know around 1, 1, we're concave upwards. We're concave upwards around 1, 1. And I show that the graph keeps increasing after that point. And you can try. I mean, you could see that the second derivative, the first derivative is 0 at that point, and for any value greater than x, the first derivative is positive, right? You put any number here, any number here greater than 1, and you're going to get a positive value. So you know that the function is increasing past 1, and it stays concave upwards past 1, because you could put any number here greater than 1, and it keeps increasing. We know this is an inflection point. But there's something interesting here. In order to we know there's an inflection point, and we also know that the derivative here is 0. So if at this point, it must be kind of flattish, right? The derivative is 0, and it's not kind of flattish. It's actually flat. The tangent line is a horizontal line at that point. The derivative is 0. So in order for the slope here to be flat, and in order for here the slope was negative, so at some point we must have another inflection point over here. So an inflection point is any point where the second derivative is 0. So let's see if we can find another point where the second derivative is 0. And sometimes people don't even go over these non-critical inflection points, but I like to because it kind of tells you when the curve kind of changes direction a little bit or changes its curvature. So let's find all of the points when that equals 0. This is the second derivative we're dealing with now. So if we have 36 x squared minus 24x is equal to 0. Let's take out a 24x. That's 24x times, what's 36 divided by 24? That's 3 halves, right? 3 halves x minus 1 is equal to 0. So the two inflection points here, either this term is 0, so we get x is equal to 0. Did I do that right? 24, divide this to this, right? 24, 36 over 24, right, 3 halves. Or 3 halves x is equal to 1. I just said this is going to be equal 0, add 1 to both sides, and then you get x is equal to 2/3. So there we have it. Our intuition was correct. There's another inflection point at x is equal to 2/3. And when x is equal to 2/3, we could try to solve for it. Let's see. It's 2/3. Well, it's too much trouble, but 2/3 is around here some point. So we have another inflection point. We don't have to be exact. We have another inflection point someplace around here where the graph changes its curvature again. So here it's concave upwards. Then it goes at this inflection point. X is 2/3. I don't know what the y value is. You can evaluate it. It turns into concave downwards. It becomes concave downwards. It flattens out there. And then the slope is 0 here, but this is also an inflection point, so then it becomes concave upwards again. So I'll do concave upwards in another color. So then it becomes concave upwards again. So the graph is going to look something like that, where the yellow is the interval over which it's concave downwards. This is an inflection. Let me draw the inflection points. I'll put an x. That's an inflection point. And then when x is equal to 2/3, that was an inflection point. This is a minimum point where we are concave. And some people don't even worry about this inflection point. But it's important to realize that there was a little interval here where we were going concave downwards. And the intuition, what's the intuition there? Well, we know we're concave upwards here. And we know we're concave upwards here. But in order for this to be an inflection point, it must have switched from concave downwards. So we know we're concave downwards here. But if this is concave downwards, there must have been an inflection point where we switch from concave downwards back to concave upwards again. And our intuition correct. There is one at x is equal to 2/3. And just to not beat a dead horse, but what are the inflection points where the second derivative is equal to 0? So that's the graph, and I think that was a fairly instructive problem. So I thank Akash for sending that to us. See you in the next video.